Let's talk about what is computational fluid dynamics, or CFD as it's usually abbreviated. As we saw in the big ideas in fluid dynamics, fluid flow is governed by three fundamental conservation laws: conservation of mass, conservation of momentum, and conservation of energy. Mathematical formulation of these laws lead to the governing equations for fluid flow, and these could be partial differential equations or integral equations. If one applied the governing equations to an infinitesimal fluid particle moving within the flow, one gets the partial differential equations. A complementary view is to apply the conservation laws to a fixed volume in the flow domain, the control volume, and in that case one gets the integral form of the governing equations. The two are equivalent. In either case, these equations are coupled and nonlinear. This means that they can be solved exactly for a ridiculously small number of special cases. These are considered in introductory fluid dynamics textbooks. In computational fluid dynamics, or CFD, we solve the governing equations approximately on the computer using software. And the software converts the governing equations to a large set of algebraic equations. That is, it uses numerical methods. It goes from calculus to linear algebra. And the large set of algebraic equations is inverted on the computer. Current CFD technology can handle flow around realistic geometries and complex physics. So you're solving very complex set of governing equations. And this is an exciting time in CFD. The CFD software we will use is ANSYS Fluent from ANSYS Incorporated. It's a leading general purpose CFD solver used in industry. And it solves the governing equations for fluid flow using a numerical technique called the finite volume method. We'll talk more about this method later. A wide range of physics can be included in ANSYS Fluent, including turbulence, chemical reaction, non-Newtonian flows, deforming boundaries, etc. We'll do a number of CFD case studies using ANSYS Fluent. We'll use it as a problem-solving platform and as a learning platform. And in doing these case studies, we will focus on understanding what's under the black box. And these fundamental ideas are applicable to other comparable commercial CFD codes. The numerical technique we will use to solve the governing equations of fluid flow is the finite volume method. ANSYS Fluent uses this method, as do many other commercial CFD codes. And the basic idea of the finite volume method is to take your flow domain and divide it into little chunks or control volumes and apply conservation to each little chunk. And you do this using the integral form of the governing equations. The net result is that you get a set of algebraic equations, and we will see this in more detail later. At this point, you might be wondering, in the structural mechanics examples, we use the finite element method to convert the governing equations to a set of algebraic equations, and why not do that here? In fact, there are codes, CFD codes, that use the finite element method. It turns out that the finite volume method is perhaps preferred over the finite element method in CFD applications. That might be because it offers one big advantage, is in that it applies conservation directly rather than indirectly. So for each little chunk, it's applying conservation, and it conserves quantities in a discrete sense, and we will unpack this idea in more detail later. This is in contrast to the finite element method, which does not necessarily conserve quantities for each little chunk or finite element. And we saw this in the case of conduction, where heat was not conserved for each little element. In our CFD case studies, we will use the finite volume method via ANSYS Fluent. We'll discuss the big ideas in the finite volume method by considering a simple example. I'll lay out what that example is in a minute. And by going to a simple problem, we can focus on the core fundamentals. More complex examples are based on these big ideas, and we'll keep coming back to these ideas as we solve problems in ANSYS Fluent. They form the building blocks of CFD and of the finite volume method. So it's important that you understand these big ideas well. Here's a problem we will use to understand the basics of the finite volume method, flow in a channel, and schematically that flow looks like this. So we have two parallel walls, one at the top and one at the bottom. We have uniform flow coming in, and at the exit we have the pressure. And typically where you have the flow leaving the flow domain, you specify the pressure. We would like to find the velocity and pressure distribution within the channel. We would also like to determine the wall friction. And once we know the wall friction, we can back out what is the power needed to pump the flow through this channel. And we'll make simplifications. And the simplifications are steady, 2D, laminar, incompressible. And these will simplify the underlying mathematical model that we need to solve. We looked at what these terms mean in the big ideas in fluid dynamics, and we'll make some of these assumptions as we go through the CFD case studies in ANSYS Fluent. So we'll come back to these terms. As we talked about in the pre-analysis, the first thing we need to do is to consider what is the mathematical model to be solved. So let's do that. The mathematical model consists of governing equations and boundary conditions. We will talk about the governing equations first, and then we'll talk about the boundary conditions. The first equation that we bring in is conservation of mass, or the continuity equation. In differential form, it looks like that, as we have talked about before in the big ideas in fluid dynamics. And that implies that the volume of a fluid particle moving within the flow cannot change. The next equation or set of equations we will bring in is the conservation of momentum, F equal to ma. And that looks like that, as we saw before. And that represents the net pressure force on an infinite small fluid particle. That represents the net viscous friction or viscous shear on the infinite small fluid particle, and these are written per unit volume. That's the acceleration, and that's the density. So that's F and that's ma, everything written on a per volume basis. And the governing equations are defined in a domain that's shown over here. So you have the top wall, the bottom wall, this is the entrance to the channel, and that's the exit. We will use a Cartesian coordinate system, so x and y as indicated here, and decompose the velocity into components in the x and y directions. So we have two components of the velocity, and then we have pressure. The unknowns are the two components of velocity and pressure, and all of these are functions of x as well as y. So we have three unknown functions, and we have three equations, one from conservation of mass and two from conservation of momentum, one each in the x direction and y direction. That completes the governing equation, so let's talk about the boundary conditions. The boundary conditions are defined at the edges of the domain. At the left boundary, we have specified the velocity. So that's velocity in the x direction, some specified value. The velocity in the y direction is 0. At the outlet, we have the pressure, and that can be 1 atmosphere. The exact value doesn't matter. At the top boundary, we have both components of velocity is equal to 0. That's a no-slip condition. And similarly at the bottom boundary. So we have 3 velocity boundary conditions and 1 pressure boundary condition. That completes the definition of the mathematical model. And there is not an exact solution available to this problem except in a region downstream where the flow becomes fully developed. And we will, discuss what the fully developed flow is a little bit later. So if you haven't seen it before, you don't need to worry about it, and we will look at it as we go through the CFD case studies in ANSYS Fluent. It's humbling that even a relatively simple problem like this does not have an exact solution, or at least a straightforward exact solution. So how can we solve this numerically? Okay, that we can do. And we will do this using the finite volume method. So let's talk about that next. If I go back to the pre-analysis framework, what we are doing is we are going to move from talking about the mathematical model to talking about the numerical solution procedure. And in particular, how do we solve this mathematical model numerically using the finite volume method? The first step is to divide the domain into multiple control volumes or cells. So you take the domain that you have, the solution domain, and you divide it into little chunks, and these are called cells, or each one of these is called a cell in the finite volume method. In the finite element method, these are called elements. So cells versus elements, it's essentially referring to the same entity. It's a different terminology. We will use each of these as a control volume, as we will see in just a little bit. And here we have divided the domain into 12 cells. The next thing we do is we reduce the problem to determining velocity and pressure values at cell centers. So I've marked out the cell centers here. I have 12 cells, so I have 12 cell centers. And at each cell center, I need to determine velocity, which I have two components, and pressure. So I have 3 unknowns at each cell center, and I have 12 cells, so I have a total of 36 unknowns. So I've reduced the problem from determining 3 unknown functions to 36 values, and that's a big reduction. And so, so we've gone from determining unknown functions to selected variables at selected points. And this process is called discretization, where you're reducing the problem to determining just a finite set of values. Cell center values are approximations of the cell average values. And this particular flavor of the finite volume method is called the cell-centered finite volume method. There are other flavors of the finite volume method, particularly the so-called node-centered or the vertex-centered finite volume, where you determine the unknowns directly at the corners of the vertices. That methodology is a variation on the cell-centered methodology. We will focus on the cell-centered methodology here, and that's a methodology implemented in ANSYS Fluent. So then the crux of the problem is, how do we determine the unknown velocities and pressure at the cell centers? Let's talk about that next. Let's talk about how to find velocity and pressure at the cell centers. We start with the mathematical model, which is a boundary value problem, differential equations plus boundary conditions. And we derive a system of algebraic equations in the cell center values from that. In our particular example, we have 36 unknown values, so we would have to generate 36 algebraic equations. And these equations are generated by performing a control volume balance for each cell. So you do a control volume balance for mass and for momentum. And we will take a look at the details of that in a little bit. Each algebraic equation will relate a cell center value to its neighbors. So if I go to our particular problem, let's say, we are looking at the algebraic equations for this cell, that those algebraic equations will, involve values at this cell center and the values at this cell center, typically. It will not involve values at, cells such as these, which are not its immediate neighbors. And we can solve the system of algebraic equations. We can invert it on the computer to get the cell center values for UVP. In our particular case, you would have to invert a system of 36, algebraic equations. Engineers are now doing problems with 1 billion unknown values. So you're inverting, 1 billion algebraic equations. And if you have a fast enough computer, in today's world, you can do that and a good solver. Everything else is extracted from those cell center values for UVP, for instance, the pressure field, the velocity field, wall shear, etc. And you do that through the process called post-processing. So that's kind of the framework of the, how you find the velocity and pressure of the cell centers and derive everything else you want to know from that. Students ask me, how is this framework different from the finite element method? The main difference is how you derive the system of algebraic equations. In the finite element method, you don't do this using the control volume balance. You do it in a different way by going to the weighted integral form and using polynomial interpolations. Here, and also the other difference is that, where we are calculating the unknowns, in our particular flavor of the finite volume method, we are calculating the unknowns at the cell centers. The finite element method, you typically do it at the nodes, which can be the corners and also the midsides. But that's a relatively smaller difference compared to how you derive this the system of algebraic equations. So the heart of the method is, in fact, this step, and let's take a look at that next. How to derive the system of algebraic equations from the mathematical model. In the finite volume method, this is done using the integral form of the governing equations rather than the differential form. So if we looked at conservation of mass, that's a differential form, and the equivalent integral form is shown over here, and that integral is applies to any particular any arbitrary controls volume within the flow domain. And this just states that the net volume flow out of any arbitrary control volume has to be 0. Similarly, for conservation of momentum, there's a differential form and the equivalent integral form, and it's the integral form that the finite volume method uses. And armed with the integral form, we apply mass and momentum conservation to each cell. If we go back to our particular example, and let's consider this cell over here, and we do a control volume balance for this cell. Let's say we do that for mass conservation, so that's the integral form of mass conservation. And so we need to know what is the net volume flow out of that cell. And let's ignore the equation right now and just do this based on physical arguments. So we want to know what is the volume flow, the rate of volume flow out of each of these segments of the control surface. Let's take a look at this particular segment. Okay. Now I need to know what the velocity is over there to figure out what is the volume of flow going out. I'll assume that the velocity along this segment of the control surface is constant and is equal to the value at the midpoint. Okay, so I'm doing averaging here, and I'm introducing an error in the process. And this value is not calculated directly, so we have to use an interpolation between the cell center values. So we just interpolate these two cell center values to get that. So when I write the volume flow contribution from this particular boundary, it will involve the velocity here, particularly the u velocity and the u velocity there. Then I go and take a look at the volume of flow going out of that boundary, and that is that's no slip, so there's no volume flow going out of there, which means that if I was doing it through the integral, then there's no contribution to the integral. Whereas when we do this, when we calculate the integral, we will interpolate between this value and this value. So you can either do it based on physical arguments, or you can go back to the integral, and for simple problems you'll get the same result. And that's the nice thing about the finite volume method, that it's very physical, and so I find it relatively straightforward to understand the big idea of it. When I'm at this boundary, I know what the velocity is from the boundary condition, so again I can calculate what the volume of flow is from the boundary condition, and so on. So I add up these four contributions and set it to 0, and that's my algebraic equation for mass conservation. Similarly, I have to do it for x momentum and y momentum, so I'll get 3 discrete or algebraic equations per cell, and I'll have a total of 36 equations because I have 12 cells. So 36 equations, 36 unknowns. So one has to average and interpolate cell center values to get values at the control surfaces, or these are called faces in the method. Okay, and we introduce an error because of the averaging and interpolation, and it's very important now what's that level of error introduced, and we will take a look at that later. And at the boundaries we use boundary conditions. And we will work through an example to get a better idea of how this works. As an example, let's work out the algebraic or discrete equation for mass conservation for one particular cell. And I'll pick this cell, and I want to know what the volume of flow crossing each of these faces is. So I have 4 contributions to the volume of flow, and I'll set that to 0 because a net volume flow out of the cell has to be 0 for mass conservation. Mass and volume are equivalent in compressible flow because they're just different by a constant, the density. Let's focus on this phase first and assume that the average value of velocity at that phase is equal to the value at the midpoint that's shown by the cross. And that's an approximation. Let me say that's cell 1 and that's cell 2. So the volume flow rate, so that's a volume of flow and that's a rate, so that's per unit time. For the phase that's between cell 1 and 2, and I'm indicating, I'm using this symbol for volume to distinguish it from V for velocity so that you don't get confused between V for velocity and V for volume. That's equal to the velocity at the green cross, which I will denote as U1-2. And velocity times the area of the phase will give us the volume flow rate. Let's say this distance is delta y. That's called a mesh spacing. This means that the area of the right face is going to be delta y times 1, and that is the dimension in the direction perpendicular to the screen. And this term will drop out of, it will be common to all the terms and will drop out. So we can assume 1 without the loss of generality. And there is an error when we write that down because we have assumed that the value that this velocity value here is equal to the average for the phase, which is an approximation. We will quantify the errors or get a better idea of the errors a little bit later on when we talk about the order of accuracy. Now this velocity here I'm not calculating directly, so I'm going to use that in term as an average between that value, and those are values I'm going to calculate directly. So u12 I will say is the average of u1 plus u2 divided by 2, and we'll assume uniform spacing for simplicity, uniform grid spacing. And in that process we introduce another error. So that's a different error, and there are two different errors coming in. Now I can use this term and put it back in here, and the volume of, the volume flow rate through that phase becomes u1 plus u2 divided by 2 times delta y, and I won't write that 1 over there. And there are two errors involved in that approximation, as we just talked about. And what I'm doing is, in the process, I'm doing that, the integral. If I did the integral form of the mass conservation, I would, that's a contribution to that integral from that phase. So I can do this based on the integral form of mass conservation or from physical arguments, and the physical arguments are a little bit easier to understand, so I'm just doing it based on the physical arguments with the understanding that the two are equivalent. Similarly, to calculate the volume of flow going through that boundary, I'll have to interpolate between the velocity over here and the velocity over here, and let's say that's cell 3. So I'll have to interpolate between, cell 1 and cell 3, particularly the v velocity, that is a velocity in the y direction. I'll let you work that out. And then the contribution from the top boundary is going to be 0, and the contribution from the left boundary is going to be known because we know the velocity coming in from the boundary conditions. So if you put it all together, we will get an equation that so the volume of flow from the right phase will involve some coefficient times u1 plus some coefficient times u2. Then from the bottom phase, I will get some coefficient times v1 and some coefficient times v3. There's no contribution from the top phase, and from the left phase I will have a constant value, so that'll just come to the right. And this is the algebraic equation for mass conservation, and I'll let you work out what the coefficients are in the exercises. An important advantage of the finite volume method is that conservation is built into the method. Or you might hear people say that the finite volume method conserves fluxes. To see why this is the case, we can go back to the algebraic equation for mass conservation that we just derived. So I'll go back to our channel flow example, and we were looking at mass conservation for this particular cell, and the form of the algebraic equation we got looked like that. So it relates velocities at these three cell centers. Here I have brought the constant term on the right hand side to the left, so I can write LHS is equal to 0. And this algebraic equation can be derived using physical arguments or by going back to the integral form of mass conservation. In either case, you get the same equation. I did it using physical arguments because it's a little bit easier to understand. As you go to more complicated situations where you are more complicated equations, say for instance, you look at momentum equation with in the presence of turbulence or something, you definitely want to do it from the integral form, since that's more rigorous. But in either case, whether you're doing it using physical arguments or whether you're doing it using the integral form, we calculate fluxes phase by phase. So we go to this phase and look at, for mass conservation in compressible flow, we look at the volume of flow crossing that phase. Similarly for this phase, and this phase. And then we add all that up and equate that to 0. This means that the amount of mass or volume leaving the control volume is equal to the mass or volume entering the control volume. It also means that the amount of mass leaving this control volume or cell will enter the neighboring cell, and there'll be no loss of mass. That means that conservation of mass is guaranteed for each control volume, and mass leaving the control volume will be equal to the mass entering the control volume. And the same idea applies to momentum and energy. So for momentum, one would go to each phase, look at the amount of, or the rate of, at which momentum is crossing that phase. Similarly for all the other phases, add them up, and for momentum it's not equal to 0, it's equal to the forces on the control volume. And so for the forces, pressure and viscous shear in this case, you would go and you would calculate the forces on each of these phases. So again, conservation is guaranteed for momentum and similarly for energy. Now conservation is guaranteed, but there is interpolation errors thrown in, which is unavoidable. But even on a coarse mesh like this, the interpolation errors won't lead to spurious non-physical results such as mass accumulating or mass disappearing from a control volume, or mass leaving a control volume doesn't match the mass entering the control volume, entering the adjoining control volume, which could be the case in the finite element method. Here's an overview of the story so far regarding discretization. So we started with the differential form of the governing equations plus boundary conditions. So that's a mathematical model we have. It's a boundary value problem. And we went over to the equivalent integral form of the governing equations, and we also have the boundary conditions. Or you could start off with the integral form of the governing equations. And using the integral form, we saw how one can derive algebraic equations relating neighboring cell center values. And that's done by performing control volume balances cell by cell. And you do this control volume balances for mass, x momentum, and y momentum in our particular example. And that's how the finite volume method proceeds. And in the cell-centered flavor of the finite volume method, the algebraic equations will relate neighboring cell center values. Let's contrast that to the finite element method, where we are given the same mathematical model. So we have the differential form of the governing equations plus boundary conditions. And from that, we would go to the weighted integral form of the governing equations plus the associated boundary conditions. So you're not going to the integral form, you're going to the weighted integral form. And using that, and this is called the weak form, and using the weighted integral form, you derive the algebraic equations relating neighboring nodal values. And you do that by assuming polynomial interpolations within each element for velocity and pressure, but also for your weights. And because of this, so in the finite element method, you're not going to each phase and you're looking at what is the amount of mass or momentum crossing that phase. And due to that, conservation is not built into the method, unlike the finite volume method. So you could get cases, as we saw in the heat conduction, where you could have heat leaving one cell through a phase, not or element not be equal to the heat entering the adjoining element. In at least simple situations, you do end up, you can show that you would end up with the same form of algebraic equations in both cases, but you will, as you go to more complicated problems, you will not get the same form for the algebraic equations, depending on the details. I should also mention that there is a finite difference method, which some of you might have seen, and that's what I was taught in graduate school, where you go directly from the differential form of the governing equations, i.e. your partial differential equations, to the algebraic equations. And this method has one disadvantage, that it cannot be easily extended to irregular meshes and complex domains. And since we have complex domains and complex geometries in real engineering applications, it's not very popular in industrial CFD codes. So we won't deal with that method over here, and we will focus on the finite volume method. Now we understand the process by which the finite volume solver derives a set of algebraic equations representing the conservation equations, conservation of mass and momentum in our case. So the problem reduces to solving a system of algebraic equations. But there is an additional complication. And the additional complication is that the algebraic equations are nonlinear. To see why we get nonlinear terms in the algebraic equations, let's go to the momentum equation, which has nonlinear terms. And in our case, the integral form of the momentum equation looks like that, as we saw before. That term represents the net momentum outflow out of the control volume that we pick. That's the net pressure force on the control surface, and that's the viscous force on the control surface. That's a nonlinear term because we have a product of velocity times a velocity component. So you have a product of two unknowns, and that's nonlinear. To see what kind of nonlinear terms we will get in the algebraic equation from this term in the integral, let's go back to our pet example and look at the same cell. And we need to do the integration in 4 parts, right? So we'll do it over this face, this face, this face, and this face. And we'll just look at how we do it for this face, and then, we can use a similar procedure for the other faces. And when we evaluate that integral over that face, essentially what we are computing is the rate of momentum outflow through that face. We're looking at the momentum, rate of momentum flow in the x direction. Let's say we'll do it in the x direction at the face between cells 1 and 2. That is equal to, rho is a constant. We're looking at the x component of velocity, and so we need the velocity over this face, and we'll assume that it's constant and equal to the value at the center like we did before. So that'll give us u12. V dot n, that's the normal component of the velocity at that face, and again, and that's in the normal is in the x direction, so that's just u, and again we'll assume that that's constant over that surface, so we'll get another u12. Essentially we are taking this, and these as constants, and so the integral applies only over ds, and that'll give us the area of that face, and that's equal to delta y times 1 in the direction normal to the screen, and we can take that as 1 without loss of generality because that will appear in all the terms. And there is an error introduced, so I'll say error 1, and that's because we are assuming that, you know, the integral over let's say the velocity over that face is just equal to the value at the center. And that's similar to the error that we had when we're doing the mass balance. And u12, and the velocity here, we'll assume, you know, we'll just interpolate between 1 and 2 like we did before. So rho u, so this velocity over here is just u1 plus u2 divided by 2. And similarly over here, so I'll just square that times delta y, and I won't write the 1, and then we have the error from before, which is error 1. But we have an additional error in, you know, assuming that the value here is equal to the average of the value here and here. And we'll quantify these errors a little bit later on. That's error 2. And when we square that out, the kinds of nonlinear terms we are going to get, so we're going to get u1 squared. So the nonlinear terms we'll get in the algebraic equation, we'll have a u1 squared term, we will have a u2 squared term, and we will have a cross product u1, u2. All of these are nonlinear terms. So then the question is how to solve a nonlinear system of algebraic equations. This is done by linearizing the nonlinear terms about guess values. So one would linearize u1 squared about a guess value of u1 and so on. And then solving iteratively, updating the guess at each time. And when the iterations converge, we have a reasonably good solution to the set of nonlinear system of algebraic equations. So we'll take a look at how we linearize about the guess values next, and then subsequently how the iterative solution procedure proceeds. Here we'll take a look at how the linearization is done so that you get a set of linearized algebraic equations from the set of nonlinear algebraic equations. I will look at one particular term, u1 squared, which is the square of the velocity there, the u velocity there, and we got that when we wrote the momentum flux through that boundary. U at any location I can split into a guess value plus a correction. So that's a guess. That's a correction. And if I had a function of u, I can write that as function of u guess plus the correction, and expand that in a Taylor series. So I'll get f of u guess plus delta u times f prime of u evaluated using the guess. So that's nothing but the derivative of f with respect to u plus delta u squared over 2, the second derivative of f with respect to u, and again evaluated using the guess, plus higher order terms. We are interested in the case here where f of u is u squared. So we look at the case where f of u is equal to u squared, and f of u guess is just going to be, so it's just going to be that evaluated using the guess. F prime of u is the derivative of that with respect to u, so that's 2u. And f prime of u evaluated using the guess is just 2u guess. If I put these back into the Taylor series expansion, I will get this. I'll get f of u is u squared, so u squared will be f of u guess squared, plus the correction times f prime of u guess, that's 2u guess, and then I will neglect this term, so I get a linearization error. Now this error becomes small as my guess tends towards the true solution and the correction becomes smaller and smaller. So I have to iterate to drive my guess to the true solution so that the correction becomes negligible, and that's where the iterative process comes in. This is the Newton's method. It's called the Newton's method. It's also called the Newton-Raphson method. And it's essentially the procedure used for linearization in the finite element case, which we talked about when we talked about that bolted flange. The two major ideas we have talked about so far are discretization and linearization. Let's put them together. So here's an overview of the two together. We talked about discretization before, and here was the overview of the discretization. And the end point of the discretization is a set of algebraic equations relating neighboring cell center values. And we derived that from the integral form of the governing equations by doing control volume balances cell by cell. And in the process of going from the integral form to the set of algebraic equations, we introduce an error called the discretization error. And I did indicate the error as we were deriving the algebraic equation for the mass balance for our particular cell. We can reduce the discretization error by using more cells in the domain, so that's mesh refinement, or we could decrease it by increasing the order of accuracy of the interpolation. And we will see that a little bit later. The algebraic equations that we have are nonlinear, so we have to linearize them about a guess value. And when we go from the nonlinear set of algebraic equations to a linearized algebraic equations relating cell center values, we introduce another error called the linearization error. And these two errors are different. And to decrease the linearization error, what we have to do is solve iteratively, and after each iteration we update the guess. And we stop iterating when our imbalances of mass and momentum are below some selected tolerance. If we had the exact solution to the nonlinear algebraic equations, the imbalances of mass and momentum would be zero. But since we have a linearization error, it's never going to be zero. But if it's below a tolerance, then our linearization error would be acceptable. Now, so this, I've seen this confusing students because they think, oh, if I refine the mesh, my error should go down. And what happens is, the iterations become actually harder to converge when you refine the mesh. So your discretization error has gone down, but your linearization error has ballooned. So these are two entities that you have to balance, and sometimes, it becomes like you reduce the discretization error and your linearization error kind of goes up. And so we will come back to this and see this when we are doing our CFD case studies in Fluent. But before that, so I want to talk about when to stop iterations, and that's an important consideration for the code user in CFD. So let's take a look at that. How do we know when to stop iterating? To understand that, I'll go back to the channel flow example. And for mass conservation for that cell, we got an algebraic equation that looked like that, of that form. And if I had the exact solution to my set of algebraic equations and I took that and plugged it into the left-hand side, the right-hand side would be zero. That would, all equal to zero, which means that the mass entering would be equal to the mass leaving in a discrete sense. But after each iteration, I don't have the exact solution to the algebraic equations. I have an approximate solution. And so my solution to the algebraic equations after each iteration will satisfy an equation that looks like that. That is, if I take my current solution after any iteration and I take the corresponding values here and plug it in here into the left-hand side, the right-hand side will not be equal to zero. It'll be equal to it'll be equal to a non-zero value, which is an error. And to indicate that this is my current solution, I will annotate it. So here's my annotation. So that's my current solution. That's my current solution for U2, current solution for V1 and V3, and they won't, all kind of add up to a zero mass imbalance. And I'm going to get a similar error for, all these other cells. And what I need is an aggregate measure over all the cells. So here's how I define an aggregate imbalance. I've written down the equation here and I'll unpack it for you. So that's an aggregate mass imbalance or a mass residual. It's also referred to as the continuity residual. Let's focus on the numerator first. What I'm doing here is I'm taking the absolute value of the mass residual for each cell and I'm adding it all up. So I'm going to each cell and I'm taking the absolute value of the mass residual and then adding it all up. And I'm taking the absolute value because whether this residual is positive or negative, it's an error. It's a mass imbalance. So the numerator gives me an aggregate mass imbalance, and then I scale it using a scaling factor. And the reason you need to scale is that what would seem like a small mass imbalance for a supersonic flow might be a large imbalance for a low speed flow. So the scaling factor ensures that what you're looking at is the aggregate mass imbalance relative to the aggregate kind of mass inflow or mass flow to each cell. We won't, I won't talk about the details of how the scaling is done and so on. It's not that important, at least at this point, and we'll deal with it when we are in the solver if we have to. And we will stop iterating when this aggregate mass imbalance is less than some tolerance. And the tolerance, the default is 10 to the power of minus 3 in the Fluent solver, and we can change that. In fact, we will do that. So that's how we'll stop iterations. And the same idea applies to the momentum equation too. So if you're looking at x momentum, the net x momentum, outflow should be balanced by the net forces in the x direction on the control volume. And any part of the momentum outflow that's not balanced by the forces is an error. It's a momentum residual. And so you can understand the momentum residual by analogy to the mass residual. Let's see how the ideas of discretization and linearization are put together into an algorithm for the iterative solution of our boundary value problem. Going back to a channel flow example with the discretization, we were looking at the division into the cells. We start by assigning guess values at the cell centers. So we would assign guess values for velocity and pressure at each of these cell centers. And we would tweak these guess values or correct these guess values using the linearized algebraic equations. And that's where the discretization would come in. And so we would go to each cell and we would tweak those guess values and say if I'm tweaking the guess values for that cell, it would involve the values at the neighboring cells. And that is, that's going to have, so my current solution after I tweaked it will have a linearization error in it. And so I need to know what the level of the linearization error is. And I assess that by calculating the aggregate mass and momentum imbalances, like we talked about. And then we check if the aggregate mass and momentum imbalances are less than a tolerance that we specify. And if those imbalances are greater than a tolerance, that means our linearization error is too large, it's not acceptable. And what we have to do is we have to go back and recorrect or retweak these guess values and recheck, if the linearization error has gone down. And if this process converges after some number of iterations, your imbalances for each, for mass, x momentum, y momentum is going to fall below the specified tolerances, and we have the converged solution, which means that now our linearization error is below a specified tolerance level, and we have a good enough solution to a nonlinear set of algebraic equations, i.e. we have an approximate solution to a boundary value problem, and this approximate solution, the linearization error is below a tolerance, and there is a discretization error, so we have to see the effect of the discretization error by refining the mesh and using more cells. Here I'm going to discuss quantifying the discretization error, which brings up a very important idea, the order of accuracy of the discretization scheme. And to explain this, I will go to the channel mesh that we had and focus on these two cells, the cell 1 and cell 2. And we had written the algebraic equation for mass conservation for that cell. And in that, we had to approximate the value at the green cross, at the the velocity, the u velocity at the center of the phase as an average of these two values. And that's the equation we had. So that's the value at the face, and that's the value at the adjacent cell centers. And in the process, we introduced an error. And here, let's quantify that error. To do that, what I will do is write the value here of u here in terms of a Taylor series expansion about the value at the face. So u1 I can write as u12, and if this distance is delta x, then that distance is delta x over 2. So first I need the derivative. So I'll need the derivative du dx, that's the derivative in the x direction, at the face at 1, 2 times this distance. That's minus delta x over 2. Because it's in the negative x direction. And then the next term in the Taylor series, so you have the second derivative times minus delta x over 2 squared, and then you also have a half. So I have a half here from the Taylor series expansion, plus higher order terms, so you'll get a delta x cubed term and so on. So I'm not going to write the higher order terms. Similarly, I can write an expansion of this value in terms of the value here. Let me write that out. Okay, so this expansion looks the same as that, except that instead of having minus delta x over 2, I have plus delta x over 2. And then if I add these two together, okay, so that'll give me 2u12, twice the value at the face, and that'll give me u1 plus u2. And let me just divide through by 2, and rearranging, I'll get something that looks like that. So I'll get u12 is equal to u1 plus u2 over 2. That's nothing but that term here, plus, now when I add these equations, these two terms will cancel, and so the leading, the next term is over here, and I will get delta, the second derivative, and this half will become 1, but then I have to divide through by 2, so I'll get a half here, delta plus dot dot dot. And this is the error term. And it's proportional to delta x squared. So the error is proportional to delta x squared because that is the leading term. And as delta x becomes small, this term in the error will dominate the other terms. And so you would say this is a second order accurate approximation. Because of that. In a first order, the error will be proportional to delta x. The delta x will be, will be in the leading term in the error. And if every approximation in your scheme is second order accurate, then you would say you have a fully second order accurate discretization scheme. And what that implies is that so let's say, I use some value of delta x and I get an error, let's say error is some value e, and if I use a new mesh that's half the old mesh, in a second order scheme, my error is going to go down by a factor of 4. Okay, because it's second order accurate, so this is going to go down as delta x squared over 2. Whereas if it was first order accurate, the error would also go down only by a factor of 2. So you can see the attractiveness of the second order scheme, that the error would go down much faster as the square of the grid spacing. But the second order accuracy has a disadvantage in that the iterations are less prone to converge, that is, it's less stable compared to the first order. So the advantage of the first order is that it's more stable, that you can drive the linearization error below the tolerance more easily as you go to more complex problems. And we will see, this relative advantages and disadvantages of the first order and second order schemes when we get into the ANSYS Fluent solver. In real life applications such as flow over a car or flow over a wind turbine rotor, we have complex flow domains, and when we mesh these flow domains, we are going to get irregular meshes. It turns out that the finite volume method can be extended to deal with irregular meshes, and this is an advantage it shares with the finite element method. And the cells can be any type of polygon in 2D. When we do the flow over an airfoil in Fluent, we are going to have a mesh that looks like that, and this is a combination of quadrilaterals and triangles. So for instance, you have a quadrilateral here. Here's a quadrilateral. Here's a triangle. And we are going to solve for the values of pressure and velocity at the centers of these cells. In 3D, the cells can be any type of polyhedron. So one could have, one typically has tetrahedrals, hexahedrals, or prisms. And whatever the shape of the cell, we would calculate the fluxes passing through each face, and we would calculate the forces on each face. So you do face by face, as we talked about in our simple example. For instance, to do the mass conservation over the cell, we would calculate the mass crossing this face, this face, this face, this face, and add that and set that equal to 0. And to calculate the mass crossing that face, we would interpolate between, say, the value here and the value at the neighboring cell center. This can be done in a couple of different ways. This would be called central differencing, and this is one way to do it in the interpolation. So we would use neighboring cell center values to get the face values, which is what we did in our simple example. And the extension to irregular meshes, conceptually, though it's straightforward, the details are very complex, and there's a lot of bookkeeping involved. But this is where it's great to have a powerful solver like ANSYS Fluent. So we will let the solver take care of the details, and so we won't get bogged down in the details. And with this level of understanding of the big ideas, we can go forth and solve exciting flow applications.